So I welcome Professor Radhakrishnan to give his speech. As I said, he will write occasionally on the board. So those at the back, if you have difficulty, you can come forward to follow the lecture.
Thank you for the invitation, and thank you all for showing up. I hope what I have to say justifies your faith. So I don't have very much to say. I'm going to tell you about one inequality, and we will try and prove that inequality, and by the end of the talk, hopefully you will see that you could have proved many such inequalities. Yeah? But we will do this using a notion called entropy, and I'll tell you what it is. Yeah? Okay, so let me just get to the problem. The Loomis Whitney inequality. Okay. So I will draw some pictures, but what's going on? There are n points in three-dimensional space. Yeah? There are some n points, and I project them down, and I see a certain number of shadows. Yeah? I may not see n shadows. Why won't I see n shadows? Because it could be that 2 points are one above the other, and they cast the same shadow. Okay? So that is, there are n1 shadows that appear on the xy plane. Now I shine the light this way, and a certain number of shadows appear on this wall, and that number is, let's say, n2, and I do it that way. Yeah, I will not do any permanent damage. So that way, and then I see n3 points on that wall, and the Loomis Whitney inequality says that n1 times n2 times n3, yeah, n1 times n2 times n3 is always at least n squared. Yeah. Once again, the picture is this. There are n points here. Yeah. I project them down. I create n1 points. I project them here, n2 points. I project them back, and n3 different points appear. Yeah. So for example, if I had 10 points all lined up vertically, yeah, 10 points all lined up vertically, how many, what is n1 then? Sorry, what is n1? All of them are vertical. I project them down. How many points do I, how many shadows do I see? 1. Okay. If I project it that way or this way, these 10 points give 10. I get 10 that side, so I get 10 times 10 is 100, which is square of n. Okay. On the other hand, if these 10 points were like this, yeah, at an angle, in a line but at an angle, then when I project, I see 10 here, 10 there, and 10 here. And then if I take the product of n1 times n2 times n3, I get 10 cubed, which is 1000, which is more than 10 squared. But the Loomis Whitney inequality says that you will never fall below n squared. Okay. And so maybe if my hand waving was not clear enough, so here is, I don't know, everybody sees this differently, but there are 3 planes here, and these beads are arranged in these 3 planes, and there are 9 beads per plane. Yeah. So if you project them, so I've lost the picture. Yeah. So if you project them somewhere, you get 9, 9, 9. Yeah. On each projection gives you 9 points, and so the total number of points is 27. n1 times n2 times n3, yeah, is 81 times 9, 729. 27 squared is 729. The inequality survives. Okay. So the question is, yeah, so unlike the physics, we are not asking about how, but why. Why is this inequality always true? And So how many of you are math Olympiad students? Yeah. So you probably proved this already, and yeah. So, but I would like to introduce today a method by which one can sort of get a feeling for why such inequalities hold, and that will be through information theory. Okay. So that's the goal. Yeah. So here is a so-called proof of this inequality, and okay, so if I have n objects, yeah, and if I want to describe these n objects to somebody, how many bits do I need to describe n possibilities? Log n bits. Yeah. If I have to describe something which is one among n things, then I need log n bits. So, all right, to describe a point, you need log n bits. To describe its projection on the xy plane, there are only n1 possibilities. So, I need how many bits? Log n1. To describe its projection on this plane, it's log n2, and to describe the projection on that plane, it needs log n3. But n1, log n1 plus log n2 plus log n3 is giving me every piece of information twice. Why am I saying this? If you look at the x coordinate of the point, it is available from two projections. Yeah? When I project down, I project on the xy plane. What information is lost when I project down? Which coordinate is lost of the point? Z is lost. Yeah? But x and y both are available. When I project along the y axis, y is lost, but x and z both are available. In the other case, x is lost and y and z. But nevertheless, x, the x value of the point, is available from two sources. Yeah? So at least like heuristically, this log n1 plus log n2 plus log n3 is giving me every piece of information that log n contains twice. So morally, now yeah, different people have different morals. Morally, I should be able to write this inequality. That is 2 log n must be less than log n1 plus log n2 plus log n3. And by now, okay, so every logarithm is to the base 2, doesn't matter, you exponentiate it, yeah, you get this inequality. Now, we did not dirty our hands with anything, Cauchy-Schwarz inequality and various things, and we just wrote this inequality, and of course, it is all nonsense, yeah, because, yeah, there is this information. What does information mean? I mean, is this mathematics? Yeah, and so we are trying to, I'll try to make sense of all this in the course of this talk. Okay. Question? For now, I'm assuming Euclidean geometry, but at the moment when I say that I project x, y, z onto the xy axis, I'm just saying I'm suppressing the z coordinate, that's all. Now, yeah, whether I got to this by a wavy form or what geometry was there and whether there was a heavy black hole there pulling my curves, it doesn't matter to me. Yeah, it's just, yeah. Again, it's all in the end just mathematics. I'm just trying to make it dramatic because I was told it's being recorded. So, okay. So, the general idea, I would like to address a philosophical issue about science, and this is something which a famous computer scientist said about the P versus NP problem, which you might have heard of, but this is not important. So, successful ideas in science are those that are pervasive and invasive, are invitingly elegant and methodical, are open to extensions and variants, and answer an objective necessity and capture a widespread but diffuse sense of dissatisfaction in a scientific community. Now, this notion of information was one such thing. People use it. We had information and quantum information even in the previous talk, and you feel that, yeah, there is something called information, but you are not at least comfortable justifying what really information means if you get down to the mathematics. And This was the situation when electronic transmission started, maybe in the early years of the last century, and one of the heroes of information theory, Claude Shannon, addressed this question and laid out what's called the mathematical theory of information. Okay? And some parts of it I would like to introduce to you today. Okay? So keep this in mind. It turns out that this notion of entropy, information, etc., it pervades many areas, and there is always a way of thinking about various things in this information theoretic way, and we'll see. But for today, I just want to prove the Loomis Whitney inequality using information theory. I already gave you what the proof is going to look like. The proof is going to be like this, but whenever somebody says obviously in the course of a mathematics proof, that is the point to be suspicious. Okay? Yeah, yeah. I mean, if it was totally obvious, usually people don't say obvious. Hence, yeah. But then when they start using the word obviously, it's a little shaky. So this obviously here is what I am trying to formalize in the course of this talk. So, yeah, and so somehow, yeah, it's customary to refer to two people in information theory. One of them is always called Alice, and the other is called Bob. I mean, once I gave a talk in Pune where Alice was, I think, Mastani and Bob was Bajirao, but yeah, but it's usually Alice and Bob. Okay, yeah. So Alice observes an outcome of some experiment, yeah? x1, x2, x3, xn. She observes an outcome of an experiment, and she would like to communicate it to Bob. Okay. So what does she do? They both sit down in advance and they agree on a protocol. So for example, Bob says, Alice, if you see x1, send me 0, 0, 0. If you see x5, send me 0, 1, 0, 1. They come up with some arbitrary encoding, codes for communicating the outcomes. Okay. And their goal is that in the end, Bob must find out what Alice observed. Okay. So the encoding should be such that when Bob receives the message, he should be able to figure out what Alice really wanted to tell him. Their goal is that they should try to encode these things with minimum number of bits, because each time they transmit a bit over a phone or some other medium, they are charged for the number of bits you transmit. Okay? Now, this need not be communication, this can even be storage. Yeah? So we observe some experiment, we put it in the computer's memory, but we might observe a color, red, and then we write down a set of bits into our computer. So we would like to encode the colors using bit strings so that we can record our information with the smallest number of bits. Okay? And so this notion of information transmission is a very important notion nowadays, and Shannon studied what is the minimum number of bits that you need to encode n outcomes. Okay. And here are the rules of the game. Alice and Bob can agree on the code in advance. Yeah? Yeah. What outcome will correspond to what code word. The code words should be prefix free. This is a slightly technical notion. Let me just tell you, it's not a big deal. So suppose I used a permanent marker or something.
No, on the board.
So suppose I said red is 0, 0 and black is 0, 0, 1. Okay. So suppose we both decide that whenever I see red, I'm going to say 0, 0, and whenever I say black, I'm going to say 0, 0, 1. Now, this is not a good idea, because if I tell you 0, 0, now you wonder if a 1 is coming. If a 1 comes, then it becomes black, otherwise it is red. So this sort of coding is not allowed. Okay? That is, when the code word ends, you should know that the transmission has ended. Okay? So such codes are called prefix free. So suppose this was 0, 0, 0 and 0, 0, 1, this is fine, because when I see 0, 0, 0, I know that it is red. When I see 0, 0, 1, I know it is black. Okay? So whatever coding they use, it should be prefix free. That is, one code word should not look like a initial part of another code word. And you cannot communicate by silence. You cannot say that, if I see red, I will say 0 within the first second, but if I see black, I will wait 4 seconds and then say 1. Okay? So you are not allowed to communicate using silence. Yeah? I don't there used to be an old Hindi song, maybe from the 70s, but I don't know who remembers. Aapki khamoshiyan bhi aapki awaaz hai. Okay? So you will be charged for talk time even if you don't say anything. Yeah? Yeah. So that is the rule that Shannon applied. And then he asked, suppose there are n possibilities, x1, x2, xn, then in the worst case, how many bits must you communicate? And many of you already said that he has to transmit at least log n bits, because the number of strings, so suppose Alice and Bob decide to use k-bit strings, they could encode one of the possibilities using all zeros, another possibility all zeros and ones, and 1, 1, 1, 1, 1, 1. How many such strings are there? 2 to the k. But they have to accommodate n possibilities. So 2 to the k better be bigger than n. So k better be bigger than log n. I mean, nothing happened. This is almost insulting to tell you this. But log n bits are needed. So what did Shannon do? Shannon asked, well, all my symbols are not equally likely. Yeah? I mean, so it's January and I want to tell my mother whether it's raining or not raining. Yeah? The chances of it raining are rather low and not raining are rather high. And there might be other n possibilities, like if she asks me, what did you eat? Yeah? So, it's unlikely that at this hour I would have eaten a samosa. I mean, at least I don't want her to know. Yeah, so the possibilities, there is a probability associated with each outcome. It's not as if all outcomes are equally likely. And in that case, should we still use code words for all the possibilities of the same length? One might assume that the outcome that is going to be transmitted more often should be given shorter code words, and outcomes that are rare can be given longer code words. And overall, our goal should be to minimize the average communication. It is as if this experiment is going to happen again and again and again and again, and usually the high probability events will happen, so we should try and minimize the encoding length for those high probability events. For the low probability events, it's okay if we assign them longer code words. Okay? And the question is, can we save, and how much can we save? And maybe an example. Yeah, actually I was told that a minister will be here, and the organizers will appreciate the fact that I use numbers which sort of flatter the ruling party. Yeah. Okay. So suppose. Anyway, these are numbers I made up. Okay. Yeah. So Anyway, so here are like 4 possibilities. I mean, I don't quite say whether it's for winning or losing, but you can, yeah. So the probability is, yeah, 0.58 that it will be BJP, it will be the Indian National Congress with probability 0.4, and these 2 parties, yeah, NCP and BCP. Now, I am observing this event somewhere, maybe Ahmedabad, yeah, and then I want to transmit this information, who won. Okay, so here is a solution. We agree in advance that if it is BJP, I will say 0, 0. If it is Indian National Congress, I will say 0, 1. If it is NCP, I will say 1, 1. If it is BSP, I will say 1, 0. These are prefix free. They are all of the same length. No question of one being a prefix of the other. So this satisfies the rules. What is the communication that I will, you know, how many bits will I send on average? Well, in each case, no matter what happens, I send 2 bits. So per outcome, it will be 2 bits. Yeah? And suppose I have to do this reporting for all the constituencies. So this experiment probably is going to be played out again and again, let us assume independently. So on average, it will be 2 bits per communication. But you know, I look at this data and say that assigning same length sequences to all of them doesn't make sense. Yeah? It is okay if I could give this fellow a very short sequence, meaning I will say that maybe when BJP wins, I will say 0. Okay? Congress wins, I will say 1, but then I get stuck. By some chance, if NCP wins something, yeah, what will I say? If I say 0, 0, that's not allowed, because 0 is already taken for BJP and 0, 1 cannot be used. What did I say? 0, 0 cannot be used for NCP. So how should I design the code so that nobody is a prefix of another, yeah, and still all events are covered and the total cost of transmission is minimum. So here is maybe a better solution, and you can think about it. This is probably the optimal solution. So what I will do is, the party which has the highest probability, I will assign a short code word. For INC, I assign 1, 0, and for NCP 1, 1, 0, and for BSP 1, 1, 1. Now notice that this is still prefix free. This is very short, but there is no other word here which starts with a 0. Yeah? And 1, 0 is shorter than these 2, but these 2 start with a 1, 1. So this is a valid encoding of these 4 possibilities. And if you compute the expected communication, it is 1 with probability 0.58, 2 with probability 0.4, 3 with probability 0.1, 3 with probability 0.1. You add this up, if I did my computation correct, it comes to 1.44, which is better than 2. Okay? So the question is, whenever you are faced with this set of possibilities and their probabilities, you can always ask, what is the amount of information that I get on learning the outcome? And you can take a pragmatic view that let us declare that the information that you get is the amount, number of bits on average that you need to transmit to communicate this information. So here was this abstract outcome with possibilities, and we are trying to quantify the amount of information in it. And let us take this engineering approach, saying that the amount of information in an abstract probabilistic system is the number of bits needed to transmit that outcome to another party. What is the best encoding that you can apply to that system of outcomes so that your transmission is as small as possible? And that we will declare as the information. You could do that, but mathematically it turns out that a certain formula associated with these outcomes is what Shannon called the entropy of this system. So let me again, I'm using a slightly scary sounding word, entropy, and of course many of you who've done physics know it from a different point of view, but they are related actually. So once again, X is this set of possibilities, x1, x2, xn, and you have associated probabilities. X1 happens with probability P1, xn happens with probability Pn. and what is the entropy of this system. If somebody communicated the outcome here, how much information did they give me? And Shannon said, measure the information by this formula. Okay, so what is this formula? So P1 log to the base 2 for some reason, because we are using binary, log to the base 2 of P1. And you add this up for each of these values. Okay. Once again, so suppose all these values were uniform, 1 over n, 1 over n, 1 over n. Yeah, if all of them were 1 over n, equally likely. Yeah, so I would like you to tell me what this equation gives. 1 over n log of 1 over n with a minus sign, log n. Yeah, so our first idea that if you have to transmit some n things, then you need log n bits. That is strictly true only if all the outcomes are equally likely. But if the outcomes are not equally likely, the number of bits you need to transmit might vary, as we saw in the election example that we had. And Shannon proposed that this quantity should be used for measuring the amount of information in a probabilistic system. And by a probabilistic system, I just mean this: some number of outcomes with associated probabilities. Okay. So are things all right so far? Yeah. Okay. Now, why this formula? What Shannon proved, what is called the Shannon's first theorem, is that no matter how you encode, you will always need that many bits. How many bits? You compute this formula. This is a lower bound on transmission. No matter how you cleverly compute your prefix free code, you will always have to send these many bits on average to communicate the outcome. Secondly, you will never need more than this plus 1. Okay? So this quantity, it is mathematically preferable. It doesn't capture the exact amount of communication, but it is within 1 of communication. And then there are certain asymptotic properties that this formula enjoys, which we will not be discussing today, which makes actually this 1 also go away. That is, in the limit, h of x is the true number of bits you need to send. What limit, what quantity, I will not tell you today. Okay. Yeah. So is this clear? Yeah. So there is a probabilistic system, n outcomes, associated probabilities. Shannon says compute this formula, summation pi log pi with a negative sign in the front. That formula captures the amount of information in this system. And there are practical justifications why this formula is very important. So this quantity h of x, which Shannon defined, measures the uncertainty in x, or the amount of information you learn when somebody tells you about x. And this h of x is a function of the distribution of x. You see, if I change these numbers, if I said that this Pn was the probability, or yeah, so for example, in the election example, if I change this probability, yeah, and then computed the entropy, it will still be the same. The entropy formula doesn't care what outcomes they are, it just says what is the distribution of numbers of probabilities that arise. Okay. Yeah. So which makes sense. I mean, we should not really care about what particular outcome the probability is associated with. And it turns out that the entropy is never more than log n, which you can sort of believe, because you will never need more than log n bits to transmit an outcome which has n possibilities. Okay. Yeah. So these are facts about entropy. I'll need to tell you one more thing before we can really do the proof of the Loomis Whitney inequality. Okay. So yes, we're going to the next level now. Yeah, but please ask. Huh? I mean, there is a lot of time, and so we talked about one outcome. Yeah? That is x1, x2, xn. Yeah, it was just x. But imagine that there are two kinds of outcomes. So let me just give you an example. This x1, x2, xn could be, one of the participants in the Olympiad. Yeah? This y1, y2, yn could be the color of their shirt. Yeah? So I pick a person at random. What is the probability that the person I pick is x1, and what's the probability that they are wearing a shirt of color red, or this person wearing a shirt of color blue, and so on. So these are the m people who are in this room. These are the colors of their shirts, and I'm going to pick one person on a certain day, and it might turn out that I pick person 1 with color red. Then this will be the probability. So this is a joint probability of two things, person, colors. Yeah? So all these numbers add up to 1. Is this clear? The total probability here, I'm going to pick a person with a shirt, and it might be this, 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 or this, and each of them has a certain probability, and the total probability is 1. Okay. So we could compute the entropy of this joint random variable xy. I have written xy, please don't think of it as x multiplied by y, x and y together. Yeah? X and y together. How many possibilities does x and y together have? M times n. There are total m times n possibilities here. One of them is going to happen. So it is the same formula of Shannon. This is the entropy of xy together. Okay. Now, if I ask this, once I give this information, there is also a distribution on x1 to xm that is created. What's the probability that I pick up this particular participant? It's the sum of these possible probabilities. Yeah. What's the probability that I pick x2? It's the sum of these probabilities. So I could compute the entropy of x alone, ignore y, compute the entropy of x alone. Or I could sum these probabilities this way and compute the entropy of y alone. So this joint system has 3 kinds of entropies that I can compute. The entropy of the combined system, restrict my attention to only the person. Persons are being chosen with various probabilities. I could compute the entropy of the person alone, or ignore the person and focus on the color of the shirt, and that would give rise to a certain distribution. That distribution would have entropy, and these things will be called h of xy, which I have written here, h of x and h of y. So what do we know? So something called conditional entropy of y given x. Okay. So there are various possible colors, various possible persons, and then I ask, once I tell you the person, how much uncertainty do you have about the color of the shirt? For example, if the person turns out to be Mimi, yeah, then a pink colored shirt is unlikely. Yeah, I don't have a pink colored shirt. So whereas if it was all participants together, I mean there are people who like pink shirts, and it could be that pink is also a possibility. Okay. But once you tell me x, the amount of uncertainty about y might change, because it could be that you picked a person and that automatically eliminates some outcomes for y. Okay. So Shannon proposes that the conditional entropy of y given x should be defined to be the amount of entropy that you originally had in the system, subtract the entropy that you got by knowing the name of the person, and the difference let us call the conditional entropy of y given x. There are other formulas for this, but for today let us just call this the conditional entropy of y given x. So what is the conditional entropy of y given x? The amount of residual uncertainty about y about the color of the shirt that remains given that I know the person. Yeah, for example, it was like the color of the pagadi. If you say Manmohan Singh, color of the pagadi, always blue. Yeah, you noticed? Yeah. No. Yeah. So the entropy of the color of the pagadi given the person, yeah, can become very small, can be 0. Actually, there is no uncertainty if the person happens to be Manmohan Singh. If it is some other person, maybe they have multiple color pagadis at home and they wear one based on their choice for the day. Good. So anyway, I hope you understand what conditional entropy of y given x means. So these are formulas. That is, if you condition, your uncertainty only reduces. Originally, when you are looking at the color of the shirt, there was certain number of possibilities, there was certain amount of uncertainty. If I tell you who is the person, then the amount of uncertainty about y can only go down. Okay, so this needs to be proved. This needs to be proved because we have, I mean, intuitively it is all obvious. Yeah, if you give me more information, how can uncertainty increase? Yeah, but since we have committed to a formula to measure information, we need to verify all these things. But this can be verified. That is, the entropy of y given x is less than entropy of y. Similarly, if instead of 2, you might have 3 possibilities. Yeah, so color, person, color of the shirt, material like cotton, or I don't know what people wear nowadays, terylene, terracotta, yeah. So the entropy in the material given the name of the person and the color, yeah. So if you add, give me more information, your uncertainty can only reduce. This was the uncertainty in the material given only the person. This is the uncertainty in the material given the person and the color. Okay. So if you give me more information, entropy only reduces. These are formulas to be verified. I would like you to accept them. Okay. Now after having accepted all this, we will go back to Loomis Whitney. Okay. So let me erase the board. Yeah, it will take me some effort. So does it erase better with water or? One second, let me try. Yeah, it's an experimental science mathematics. Yeah. Yeah, can you try? Yeah. Okay. So yeah, so while the board gets erased, so all right, so we had these, recall the Loomis Whitney inequality, we had n points, their projection was n1 this way, n2 that way, n3 that way. Okay. There was no probability. I mean, we were supposed to prove this inequality, there was no probability. Okay. I am going to impose a probability on this system just because I am comfortable with information theory and I know some inequalities in information theory, and I insist that I use those inequalities to prove Loomis Whitney. Okay. Yeah. So I pick a point uniformly at random from these endpoints. Now what does a point in 3 dimensions mean? It consists of 3 quantities. A point in 3 dimensions consists of 3 quantities, x, y, and z. So the entropy of the point P, to say the entropy of the point P means the entropy of x, y, and z. And what is the entropy of x, y, and z? Well, how much uncertainty is there in x? How much uncertainty is there in y after knowing x? And how much uncertainty is there in its z coordinate after knowing x and y? Yeah. So if I, is this clear? Yeah. Okay. So I picked a point P at random, one of the n points, and I picked a point P here, and the amount of entropy in this, there were n points. So the amount of entropy was, since I am picking uniformly, when I pick out of n outcomes uniformly, the amount of entropy is log n. Okay. Now I project it down, and this point is my point P1. And what relation does it have to P? We have just suppressed the z coordinate. Projecting down means suppressing the z coordinate. That means it is just the entropy of x and y itself. And the entropy of xy is entropy of x plus entropy of y given x. This was our definition of conditional entropy. Conditional entropy was this minus this. So this is actually an equality, although I have written inequality, this is actually equality. Okay. Actually all these are equalities. Entropy of P2 is entropy of x and z. So I have suppressed the y axis, y coordinate. So entropy of x plus entropy of z given x. And entropy of P3 is entropy of y and entropy of z given y. Okay. So is this clear? I mean, yeah, nothing has happened. Now let us compare the sum of these three quantities and this quantity. H of x, so I am asking you to add these inequalities. Yeah? H of x appears once here. In this mess, H of x appears how many times? Twice. H of y given x appears once here. It appears once here, and once it is H of y. But we know that H of y is H of y is greater than or equal to H of y given x. So the total contribution here is at least 2 times this. One contribution is directly available, another contribution is H of y. This is conditional entropy, this is full entropy. Full entropy is bigger than conditional entropy. So this quantity is bigger than this. What about this? This is H of z given xy. This is H of z given x. This is H of z given y. This is the amount of uncertainty in z. I am just repeating myself. The amount of uncertainty in z after knowing both x and y. This is amount of uncertainty in z after knowing x alone. So this quantity dominates this quantity, is more than this quantity because of some formula that I had written in the previous page. This quantity also dominates this quantity. So what is the net result? The total amount of entropy in these 3 points, the entropy of P1, entropy of P2, entropy of P3 is twice, at least twice, the entropy of P. Okay. Now, we have set up our experiment with uniform distribution. So entropy of P is exactly log n because it is uniform. What about entropy of P1? Well, P1, yeah, log n1, well, is it equal to log n1? Well, it is a distribution. P1 is one of these n1 points, but it may not be the same, it may not be uniformly distributed. For example, suppose the original n points were like this heap of points here, then the points in the center have much more chance of occurring because there are lots of points over them, whereas points around have lower, but it is some other crazy distribution on these n1 points, but it has only n1 outcomes. And if an experiment has only n1 outcomes, its entropy is at most log n1. Yeah, yeah, and similarly log n2 and log n3, which is what I've written in the next slide. So by direct inspection, yeah, no calculations, we observed that 2 times H of P is less than this, term by term matching, and then this is equal to 2 log n, this 2 is the same 2, this is log n because we by decree said it is uniform distribution. We designed our experiment that way. So this is equality, this is an upper bound on H of P1 because if an outcome has only n possibilities, it can have an entropy at most log n. So this P1 can have entropy at most log n1, this has at most log n2, this has at most log n3, and now you rearrange this inequality and you get this. So we started with what appeared to be some hand wavy argument where at some point we said obviously, etc. But if you use Shannon's formula, that obviously can be made rigorous and you can extract the Loomis Whitney inequality. All right. So once again I would like to, yeah. So this formula captures the intuitive understanding of information. We defined conditional information in this way, and there are just other justifications for why conditional information should be defined like this. the entropy is maximum when the outcomes are uniform. Okay, that is the most uncertain situation. And we justified the Loomis Whitney inequality using basically these considerations. Didn't really have to dirty our hands with actual numbers and fancy inequalities, but all that is hidden inside the fact that conditional entropy is less than entropy. Okay, in proving that, somebody has done the hard work, but now you internalize it and use it. Yeah, okay. And now there are many other combinatorial identities, and there is an excellent survey article by David Galvin, and I invite you to look at it. Now, entropy shows up in many places, and in other contexts there are many other situations in computation where this sort of entropy makes its appearance. So I'll just flash the thing that I wrote before. So it is pervasive, it is invasive, it is elegant. I hope you liked that everything turned out neatly, and it's widespread. It does capture a certain dissatisfaction in the scientific community. Okay, so I think Shannon should be one of the heroes of our time. I have found entropy in unlikely places. For example, I found it in Mumbai Mirror. Yeah, so about 2 years ago, I tried to solve this puzzle. I don't know how many of you read Mumbai Mirror, and I usually try to find the longest word, and I found poetry, and I was really thrilled. Yeah, poetry. How often do you find poetry? But then I counted, and it didn't include all the letters, and you won't believe me, I spent like about 20 minutes trying to look for the word, and then it turned out that it was actually entropy. Yeah. So yeah, so I've been after that saying that I used to be satisfied with poetry until I found entropy. Yeah. So yes, I'll be happy to take questions, and I of course only scratched the surface, but I hope it was useful. Yeah. Question.
I have one question. When does equality occur in the inequality? What type of distribution will give rise to equality of the point?
So, yeah, so I think we can, so the lazy answer is that wherever we used, so there are so certain variables should be conditionally independent given certain other variables, then equality will appear, but I haven't pinned it down. Yeah. There are continuous, Loomis Whitney's inequality is actually an inequality in the continuous setting. I've presented the discrete version. That is, if you have a certain volume in space, then you compute its area, and then you multiply the product of the areas, it will be at least this. By the way, suppose this was, so here's a quiz now, yeah, since you have any questions? Yeah, question.
Sir, the definition of Shannon entropy that you gave,
yes,
that is a good measure of the information, or rather the lack of the uncertainty.
Yes.
But how do we reconcile this definition with our concept of entropy? Because in classical thermodynamics, we have a certain axioms for entropy, like monotonicity, positive derivative, etc.
Yeah.
So does it also have some analogs like this?
So actually, I don't know that much about Boltzmann definition of entropy, but I think that also talks about log of the number of possibilities. Yeah, and in that sense, it is the same. Now, Shannon entropy, if you repeat an experiment many times and ask where most of the probability resides, it turns out that the number of outcomes grows exponentially, but the constant in front of the exponent is the entropy. It is the rate of growth after taking logs. But unfortunately, I won't be able to give you a completely precise answer about how this ties to the physics notion of entropy. Sorry.
Yeah.
Question, yes? Yeah. Professor.
Yeah, I think this is along the line what the person asked. So but this may appear very strange. So I understand it's a information theory system, nothing to do with physical system as such, but I'm following the idea of Bekenstein. Bekenstein proposed entropy for black hole out of the blue completely. Something strange happening in dynamics of black hole. He said it looks like entropy we are familiar with, and he was ridiculed. He was saying, now you are talking entropy, next day you will ask me what is the temperature. So he said, maybe yes, I will ask you. So can I just say same thing now, since you have entropy of a information theory system, can one associate,
can you take a derivative?
Temperature, yeah, some kind of volume of information and change in energy cost or something like that.
Yeah, so that, I mean, so there are, those are studied in the information theory. I mean, the word temperature is not used, but the derivative of the entropy and things like that are of consideration even here.
So okay. Some kind of energy cost is.
That's right.
Okay, thank you.
Yeah. Any more questions from the students?
What is the difference between entropy and information? Are they the same? You're using it interchangeably?
For me, it is the same. So given a probabilistic system, the information, uncertainty, entropy, they are the same for me.
Other questions?
Same thing. Yeah.
1 by n is the disorder, then 1 by n equally probable is the
most disordered, but this is a measure of disorder, yeah.
Okay.
So, yeah, so question.
So I'm not able to figure this out or get my head around it. The equation you wrote for conditional entropy.
That's right.
So, I mean, the example that you gave, obviously the uncertainty depended on x.
That's right.
So, how can you write something general?
How can I write like that? Yeah,
Mm-hmm.
That's correct. That's a very good question. Where did it go? Yeah. So, yeah, thank you. It's amazing. So, X has various possibilities. This is the person that we pick, and then once we pick a person, that person might show up wearing this color shirt, this color shirt, this color shirt, or this color shirt. Whereas this person always likes to wear shirts of only one color. Okay, this, whenever you have two variables x and y, this is the picture you should have. Each of these branches has an associated probability with it. Each of these branches has what is called the conditional probability associated with it. Now, if it is this person, if you ask what is the residual entropy, it is the log, it is the formula applied to this conditional distribution. If it is this person, it is this. So, when I say what is the conditional entropy of y given x, you have a valid question. Which x? If it was this x1, the answer is different. If it is x2, it is different. If it is x3, it is 0. Yeah? Because there is no uncertainty about the color of the shirt. So what do we mean by h of y given x? Stated that way, h of y given x is compute this entropy, compute this entropy, compute this entropy, compute this entropy, and take their average weighted by the probabilities that you wrote here. With what probability does this become your residual entropy? With what probability that this become the residual entropy, and so on, and that average. It turns out that with that definition also this formula holds. So that's an alternative definition of conditional entropy. Now it is no more clear why the average should be less than the whole. Yeah, I mean so this is when I ignore x1 and look at the average of these distributions. Why should that entropy be more than this entropy? This is what is called, so this is because of the convexity of some function. So what's called the Jensen's inequality or something like that will be used in the proof of this. Not a big deal, but you prove all that 70 years ago, yeah, and then keep using it, yeah. but I have a quiz. Yeah. So suppose the same question, I did it in d dimensions. There were points in d dimensions. Yeah. Project it, remove one of the coordinates, suppress one of the coordinates, I get n1. Suppress another one, I get n2. Suppress another one, I get nd. Yeah? There are d such projections my point will have. Yeah? And there are n1 different shadows on this plane, n2 different shadows, and d different shadows. Now, the total number of points was n, and I write n1 times n2 times n3, n to the power d. What should I write as the exponent here? And why? Because every piece of information, yeah, the x coordinate is lost only in the projection along the x-axis. In every other d minus 1 projections, that information is available. So every piece of information that is there here is available d minus 1 times here. So you get to write d. Okay. Yeah. So many such inequalities can be proved directly from considerations of information. Thank you very much. I've gone over time.
Yeah, any other questions? Okay, if there are no other questions, let's thank Jaikumar once more for his speech and both the speakers of this morning. Thank you. And right now we have a break, a tea break outside, and then we come back for the formal award function at 12 o'clock.